Hello friends, I hope you are able to understand my previous lecture. Today we will discuss about some more examples of contour integrals. In the last lecture we had discussed how to evaluate contour integrals. So to evaluate contour integrals you just have to convert your complex function from complex variable z to real variable t. So we have seen how to convert given complex function into one real variable. So for that we are using parameterization of this curve C or contour C. So from the parameterization of contour C we are able to convert this integral from complex variable z to real variable t. So today we will see some more examples on this complex or contour integrals. Okay, so we had discussed about this example in the last lecture. Today we consider one more example. Suppose our function is defined in this way. F of z is 1 when y is negative. Y is negative means your complex number is below x-axis. This is x-axis. So if complex number is below x-axis, y will be negative. In this portion y is negative. So if complex number is below x-axis, value of function is 1, and if complex number is above x-axis, that is when y is positive, means in this part, upper half plane, then value of function at that complex number is 4y, and our contour is the arc. Arc means portion of the curve. Contour is the arc along this curve y equal to x cube. So it is given that contour C is from this point z equal to -1 minus I to z equal to 1 plus I along y equal to x cube. So you are familiar with the graph of y equal to x cube. Here I have just given the rough sketch. So this is the curve y equal to x cube, and we have sketched here the portion of this curve from z equal to -1 minus I to z equal to 1 plus I. This is not minus. Okay. From z equal to -1 minus I to z equal to 1 plus I, and in counterclockwise direction. So this is our rough sketch of curve C. So contour C is the arc from z equal to -1 minus I to z equal to 1 plus I along the curve y equal to x cube. So depending on the location of our complex variable z, our function is defined in this way. So if our complex variable z is in this part here, then value of function at that complex variable is 1. So if z is here, if z is in this part of the arc, then f of z is 1. If z is in this part of the arc, then f of z is 4y. So I have to break this curve y equal to x cube into two parts. Okay. From -1 minus I to 0 and 0 to 1 plus I. Here graph of y equal to x cube is continuous, but function is different in two different portions of this curve. So I have to consider contour integral along this part from -1 minus I to 0 and along 0 to 1 plus I, because function has different value in different parts of the curve. So we consider two subparts of this curve. So given contour is z equal to x plus I x cube. Okay, we have converted in terms of x variable. Along the curve, along this curve, y equal to x cube. So this is the representation in terms of x variable. Z is x plus iy, and putting y equal to x cube, we write z equal to x plus I into x cube. And x runs from -1 to 1. You can see at this point value of x is -1, and at this point value of x is 1. So x is from -1 to 1. So this is the parametric representation of given contour between x equal to -1 to 1. So we are using x as a parameter. Instead of x you can use t also. If you are taking x equal to t, then it will be z equal to t plus I t cube, where t is from -1 to 1. So this contour consists of two contours. Okay, I have divided into two sub contours because along these two contours value of function is different. Value of function is different in this part, and value of function is different in this part. Okay, so therefore we have to divide our curve into two sub curves. So first we consider this portion when x is between -1 to 0. So we consider this part as C1 from -1 to 0, and from 0 to 1 we consider C2. So if we consider parametric representation for C1, then value of y is same either for C1 or C2. So y equal to x cube, but along C1 our curve is from -1 minus I to 0. So at this point value of x is -1, at this point value of x is 0. So x is from -1 to 0 if we are on C1, and along C2 x is from 0 to 1. This is C2. So from this point to this point x is from 0 to 1. So I have to consider integration of f of z along C1, then along C2, and then I have to take their summation. So along C1, as we discussed, y is x cube and x is from -1 to 0. Now if z is x plus iy, dz is dx plus I dy, and from this we obtain dy equal to 3 into x square dx. So this we can rewrite as 1 plus 3ix square dx. Now along C1 x is negative. So if x is negative, cube of x is also negative, and y equal to cube of x. So y is negative. Or it is obvious that along C1, if we are on C1, then we are below x-axis, and below x-axis y is negative. So y is negative. So if y is negative, it is given that when y is negative, value of function is 1. So we take f of z equal to 1 along C1. Similarly along C2, y is x cube, but x is from 0 to 1. Along C2 means we are here. So along C2 we are from having x from 0 to 1, and along C2 x is between 0 and 1, so x is non-negative, that means y is non-negative. So f of z is 4y. It is defined in this way: if y is positive, f of z is 4y, and y is x cube, so f of z becomes 4x cube. Now integral along C is equal to integral along C1 plus integral along C2. Now along C1, x runs from -1 to 0 and f of z is 1. So we consider f of z equal to 1. X runs from -1 to 0. dz is same along both the curves. dz is 1 plus 3ix square dx. The same thing here. So dz is 1 plus 3ix square dx. Along C2, f of z is 4x cube. So here I put 4x cube. Okay, now this is these are simple integrals of real variables. Here x is real variable. Okay, so this we can rewrite as or by direct integration of 1 with respect to x is x. This is going to be x cubed by 3. So 3 will cancel out and x is from -1 to 0. Here we consider 4 outside. We multiply this bracket by x cube. So it is x cube plus 3i x raised to 5. Here we put upper limit x equal to 0 minus lower limit is -1. So this is -1. Cube of -1 is -1. So -1 minus I plus 4. Integral is x raised to 4 by 4 and this is x raised to 6 by 2. 6. So it will cancel out 3. So after simplifying we will obtain 2 plus 3. So be careful whenever you are having the equation of curve same. Your equation of curve is same either in this part or in this part. But value of function is different in two different parts of the curve. Therefore we have taken integral along two different sub-curves. So let us take another example. Here function is x square minus I y square and contour is along the parabola y equal to 2x square from order pair 1 to 2 order pair 2 8. So this means x is in between 1 to 2 and y is in between 2 to 8. So we can represent in terms of parameter x. We have y equal to 2x square. So we can put y equal to 2x square in z equal to x plus iy. So z is x plus iy and y is 2x square. And here you can see value of x goes from x equal to 1 to x equal to 2. So it is from 1 to 2. Or you can observe in this way also. Okay, this is y equal to 2x square, rough sketch. Here x, so we have to consider this part of the curve. Part of the curve y equal to 2x square between x equal to 1 and 2. So this point is 1, 2, this is 2, 8 and we are going in this direction. Okay, and if you are comfortable, this is fine. Put y equal to 2x square in z equal to x plus iy. And what about x? So our curve is starting from this point. So at this point value of x is 1 and this is the end point of the contour. So at this point value of x is 2. Okay, so x is from 1 to 2. Now you know how to find out dz and all these things. dz is dx plus I. This is going to be 4x dx and this you can rewrite in this way. Function is x square minus iy square. So we put y equal to 2x square here. So after putting y equal to 2x square we will obtain this. So function is converted in terms of x. dz is also in terms of x and x is from 1 to 2. So finally our contour integral becomes integral of function of only one variable x and x is from 1 to 2. Okay, so after evaluating this you will obtain your integration. So next example, suppose I consider a z bar square. Function is z bar square. So evaluate z bar square dz along the shortest path joining the endpoints. Endpoints are 0 and 2 plus I. So what is the shortest path between given 2 points in the complex plane? So the shortest path is, as we know, joining 2 points is straight line. So we have to find out straight line joining these 2 points. So this is 0, 0. This point is origin. So we have to consider straight line from 0, 0 to 2 plus I. And what is the equation of this straight line? So you can see here z is 2, x is 2, y is 1. So x is double than y. So equation of straight line is x equal to 2y. It will satisfy this. If I put x equal to 0, I will obtain y equal to 0. So I will obtain this point. If I put y equal to 1 here, I will obtain x equal to 2. So I will obtain this point 2, 1. So this is the simple equation of straight line passing through origin. So along this straight line we can put x equal to 2y. So z becomes x plus iy is x is 2y. So it is converted in terms of only one variable y. Now at this point value of y is 0, and at this point value of y is 1. So y is from 0 to 1. So here we have converted in terms of parameter y. dz will be z is 2 plus I into y. So dz is 2 plus I dy. Function is z bar square. So if z is x plus iy, z bar is x minus iy. And we first put x equal to 2y. So 2y minus iy whole square. Now you can take y common. So y square into square of 2 minus I. So after simplifying this, you will obtain this. So you can see z bar square is converted in terms of only one variable y. Y is from 0 to 1. So using all these things, we will obtain this. Now 3 minus 4i 2 plus I is constant. Integral of y square is y cube by 3. Okay, so this is along the value of contour integral along the shortest path joining the endpoints. Next example. Function is z minus z0 to the power n, where z0 is a fixed constant. And what is the contour? Contour is the circle of radius r with center as z0. Taken in positive sense means in counterclockwise direction. So we know that parametric equations of circle are z equal to radius into cos theta, radius into sin theta. And as we had discussed in the last lecture, if you have any circle with center z0 and radius r, you can represent it parametrically in this way. Z minus z0 equal to r into e raised to it, or r into cos t plus I sin t. So here you have to evaluate along the whole circle. So we have considered parameter t from 0 to 2 pi. So we find out what is dz. So dz is going to be, this is constant, so derivative is 0. R is constant, derivative of e raised to it is e raised to it into I dt. And we convert our function in terms of t. So our function is z minus z0 to the power n. So we put z minus z0 equal to r e raised to it. So this is going to be r to the power n e raised to I n t. So everything is converted in terms of t. T is from 0 to 2 pi. This is z minus z0 raised to n is r raised to n e raised to I n t. dz is I r e raised to it dt. I is constant, r raised to n plus 1 is constant. And you know how to integrate this. It is e raised to I into n plus 1 into t divided by coefficient of t, that is I into n plus 1. I will cancel out here and we consider n plus 1 outside. Upper limit is t equal to 2 pi. So we put e raised to I n plus 1 into 2 pi minus e raised to 0 is 1. Now this is going to be create a problem if n is minus 1. If n is minus 1, then this will become infinity. So this is undefined if n equal to minus 1. So here you have to must write this is valid if n is not equal to minus 1. We will see what happens if n equal to minus 1. Now using Euler's formula, we know that Euler's formula is e raised to I theta is cos theta plus I sin theta. So here theta is 2 pi into n plus 1. So using Euler's formula we can write cos 2 times n plus 1 pi plus I sin 2 times n plus 1 into pi minus 1. Now we know that if we have even multiple of pi, then this is 1 and sin n pi is 0. So this is 1 and we have negative 1 here, so it will become 0. So if n is different from minus 1, value of this contour integral is 0. Now what if n is minus 1? So we consider n equal to minus 1 here and we calculate separately for n equal to minus 1. So for n equal to minus 1, if I put n equal to minus 1 here, I will obtain r raised to minus 1 e raised to minus it I r e raised to it dt. Okay, so I put n equal to minus 1 in 1 and I obtain this, taking n equal to minus 1 in that equation 1. So you can see this is going to be e to the power 0, that is 1, r to the power 0, that is 1. So we will have I and integral from 0 to 2 pi, integral of 1. So it is going to give me 2 pi I. So if n is minus 1, this is 1 upon z minus z0. So if n is minus 1, value of integral is 2 pi I. So if n is different from minus 1, value of integral is 0 along the circle, and if n is minus 1, value of integral is 2 pi I. Next problem. Function is z bar, c is the right half of the circle, mod z equal to 2. Mod z equal to 2 means circle with center, origin and radius 2. From z equal to minus 2i to 2i. Okay, so it is like this. This is the circle, but we have to consider the portion of the circle from z equal to minus 2i to z equal to 2i. So what is parametric representation? Circle is mod z equal to 2. So as we discussed in first lecture, we can have this type of parametric representation, z equal to 2 e raised to it. That means z equal to 2 cos t plus I into 2 sin t. We are using parametric equations of circle. This is in terms of x and y. This is going to be x square plus y square equal to 4. And we know that parametric equations of x square plus y square equal to 4 are x equal to 2 cos t, y equal to 2 sin t. So z is going to be 2 cos t plus I into 2 sin t, that is 2 into cos t plus I sin t, that is 2 into e raised to it. This we had already discussed in the previous lecture. But we don't have to consider the whole portion of the circle. Okay, our circle is the right half of the circle, mod z equal to t, 2, from z equal to minus 2i to z equal to 2i. Okay, so this is our contour, right semicircle. So at this point, what is value of t? So value of t at this point is minus pi by 2, and at this point t is pi by 2. If I put t equal to pi by 2 here, I will obtain z equal to 2 into cos pi by 2 plus I sin pi by 2. Cos pi by 2 is 0, sin pi by 2 is 1. So I will obtain this point 2i. Similarly, I will obtain this point minus 2i if I put t equal to minus pi by 2. So t is from minus pi by 2 to pi by 2. So once you have parametric representation, now things are easy. You know how to find out this dz. dz is going to be 2i e raised to it dt. Z bar is nothing but conjugate of this. Conjugate of this. So 2 into e raised to minus it. and put all this in terms of t here. Everything is converted in terms of t. Z bar is 2 e raised to minus it. Dz is 2I e raised to it dt. Okay, this is going to be 1 e raised to 0, and 4I t is from minus pi by 2 to pi by 2. So you will obtain 4 pi I. Now you are asked to calculate, you are asked to find the value of this function 1 by z along C. So you can see 1 by z, f of z is 1 by z along C. So along C, all the values of z are non-zero. Z is different from 0 along C. That means function is defined along C. Now using this integral, you have to find out value of integral of 1 by z along C. So how to evaluate that using this integral? So we are going to use this property of absolute value of complex number. We know that z into z bar is square of mod z. So z bar can be written as mod z square divided by z. Now along our contour is circle, and radius of circle is 2. So along contour C, we know that if any point z is along C, its modulus is 2. So along C we can write mod z equal to 2. So I have written mod z equal to 2 here. So I will obtain z bar equal to 4 by z along C. Now this we have obtained, integral is 4 pi I. So now along C, z bar can be written as 4 by z. So I put z bar equal to 4 by z here. 4 will cancel out and I will obtain value of 1 by z is pi into I. So this is interesting. You know what is integral of z bar along this, and you are able to find out integral of 1 by z along C. This is another exercise you can do on your own. Integral of z bar along the straight line from z equal to 1 minus I to z equal to 3 plus 2I. You first have to find out the equation of straight line joining these 2 points, and then try to convert either in terms of x or y or in terms of parameter t. We consider this problem. We are given 2 different curves between these 2 points 0 to 1 plus I, and we have to find out value of this in this evaluation of this in function of z along 2 different paths of integration. So f of z is x minus y plus I x square, and you have to evaluate this integral along the straight line from z equal to 0 to 1 plus I. And another path is, you can see here, first path of integration is from z equal to 0 to 1 plus I, so along y equal to x. Second path is first along this path from z equal to 0 to 1, and then from z equal to 1 to z equal to 1 plus I. So second path of integration is along the real axis from z equal to 0 to 1, and then along a line from z equal to 1 to z equal to 1 plus I. Okay, so function is same, but we are considering value of contour integral along 2 different paths. So whether we are going to obtain the same answer or different answers. So let us see. First we find out value of contour integral along the straight line from 0 to 1 plus I. So along this path. So straight line from 0 to 1 plus I is nothing but y equal to x. So we can consider this as line segment OP. So parametric representation is z equal to x plus I by but y is x, so I put y equal to x. And at this point value of x is 0, at this point value of x is 1, so x is from 0 to 1. So along OP, dz will become 1 plus I to dx. Function is x minus y plus ix square, so we put y equal to x. So function will become I into x square. So along OP, you know how to evaluate this. So if you evaluate along OP, value of contour integral will become I minus 1 by 3. Now in the second part, path of integration is consisting of two line segments. Line segment from O to M and line segment from M to P, and both are having different equations. Along OM, value of y is 0, and along MP, value of x is 1. So we have to find out integration along OM and integration along MP, and then we have to add those two integrals. So along OM y is 0. So z will be x plus iy, that is z will be x. So we put z equal to x along OM, and x is from 0 to 1 along OM. So function will be f of z is, put z equal to x along OM, y is 0. So here we put y equal to 0. So f of z will become x plus ix square. Similarly, along line segment MP, you can see x is 1 along line segment M to P. So x is 1. So x becomes constant, y is changing. Y is changing from y equal to 0 to 1. So limits of y will be from 0 to 1. And we have to put x equal to 1 here. So it will be 1 minus I plus I. So along line segment MP, x is 1. So we put in z equal to x plus iy, we put x equal to 1. And y is from 0 to 1. dz will be, this is going to be 0, I dy. F of z is 1 minus y plus I. Okay, I have taken x equal to 1 in the expression of f of z. So integral along given contour is integral along OM plus integral along MP. And after substituting all these values, you will obtain this value. So you can see both are different. Integral along path in part A is different from integral along path in part 2. So what this indicates? This indicates that integral of same function along two different paths of integration may be different. Okay, so the value of contour integral depends on the path of integration. If we change the path of integration, contour integral may be different. Okay, so this is important. Line integral or contour integral depends on the path of integration. Integral of f of z from one point to another point, say z0 to z1, can be different along two different paths joining z0 and z1. Okay, so similarly you can do more exercises. We stop here. In the next lecture we will discuss some important inequalities. One is known as ML inequality. Okay, so I hope you like this lecture. If you have any doubt, you can comment or you can write to me on my email address. Thank you very much.